it is a stunning fact that a tiny visitor from another star system can hold the keys to rewriting our textbooks. Tonight, we begin with the latest definitive look at an object that continues to captivate everyone from professional astronomers to passionate space enthusiasts. 3I ATLS. On November 30th, 2025, a critical observation was made. The Hubble Space Telescope, using its wide-field camera 3, successfully captured a fresh image of this interstellar object after it had passed its closest point to the Sun, known as post-perihelion. At the time this photograph was taken, 3I Atlas was approximately 286 million kilometers away from us here on Earth. What the image shows is the object surrounded by a glowing, teardrop-shaped halo, or coma. Notably, it also displays a subtle extension of material pointing back towards the Sun, a feature famously known as an anti-tail. If you look closely at the photograph, the distant background stars appear as streaks across the frame. This is actually a testament to the telescope's tracking capability. It was locked onto the fast-moving comet, effectively isolating the comet itself as a very compact and distinct source of light. The importance of this particular image is found not just in its clarity, but in the specific details it unveils. That teardrop shape isn't some random visual trick. It directly reflects how the material is distributed around the comet's nucleus. The anti-tail, for instance, extends an astonishing 60,000 kilometers back toward the Sun, while the overall radius of the coma surrounding the nucleus is measured at about 40,000 kilometers. Crucially, this structural configuration perfectly aligns with predictions that were made in a recent scientific paper. That paper had analyzed the non-gravitational acceleration that 3I Atlas was undergoing. According to those intricate calculations, a dense swarm of microscopic, non-volatile objects separated from the main nucleus during its closest approach to the Sun. This separation event produced an elongation of material, which is precisely what now appears as the anti-tail in Hubble's new images. The fact that the observed separation matches the predicted position of this swarm offers a powerful confirmation of the proposed physical model. Now, let's look back for a moment. Prior to its perihelion passage, Hubble had imaged 3I Atlas back on July 21, 2025, as it was still approaching the Sun. At that time, the object was at a distance roughly 56% greater than the post-perihelion distance. Even then, the anti-tail was already visible, although the comet was naturally smaller and fainter due to its distance. The brightness contours in that image clearly showed a distinct elongation of scattered sunlight pointing in the sunward direction, a complete reversal of what we typically see in comets born in our own solar system. Standard comets form tails that are pushed away from the Sun by the solar wind and radiation pressure. The fact that 3I Atlas continues to defy this expected pattern strongly reinforces its classification as an interstellar object with genuinely unique properties. These high-resolution Hubble observations are beautifully complemented by the work of amateur astronomers around the globe. Large-scale images captured with smaller telescopes are able to extend the observed field around 3I Atlas out to millions of kilometers, giving us a complete view of the broader dust and gas environment surrounding the comet. One especially notable observation was recorded on December 2nd, 2025 by a 12-inch telescope located in Farm Tivoli, Namibia. By using long exposures, this single capture produced a field of view covering an immense 6.1 by 9 million kilometers at the comet's distance of 280 million kilometers from Earth. This powerful amateur image reconfirms the presence of the Sunward Anti-Tail and provides vital data points for accurately measuring the full extent of the coma and how it is interacting with solar radiation. The scientific importance of these continuous observations goes far beyond just taking pretty pictures. Hubble's post-perihelion data provides crucial constraints on the physical structure and how 3I Atlas is evolving. By meticulously measuring the brightness distribution inside the coma and precisely mapping the anti-tail, researchers are able to model the object's mass loss rate, the size distribution of the particles being ejected, and the overall dynamics of that released material. These models, in turn, inform our understanding of the object's actual chemical composition, which is still being determined. Ultraviolet spectroscopy data is eagerly anticipated as it will reveal the exact composition of the gas plume around 3I ATLAS. Once released, this spectral information will allow scientists to definitively identify the volatile compounds driving the comet's activity, whether those are water, carbon dioxide, carbon monoxide, or other exotic substances. It is important to remember that observations of 3I ATLAS are not limited to just Hubble. Coordinated global campaigns involving space-based and ground-based observatories are actively monitoring the object. Facilities across Europe, Chile, Hawaii, and Australia are capturing images, spectra, and astrometric data. The goal of these massive campaigns is multifaceted to precisely track changes in brightness and morphology, to nail down the composition of the coma, and, critically, to detect any measurable non-gravitational acceleration. Each piece of this data provides critical insights into the object's physics, helping to determine if it truly behaves like a known solar system comet or if it represents a fundamentally different class of interstellar visitor. The non-gravitational acceleration is especially important for fully understanding the object's current behavior. As material is ejected from the comet, it creates a subtle but measurable propulsive force that slightly alters the object's expected trajectory. In the case of 3I ATLAS, the observed acceleration away from the Sun is consistent with that core hypothesis that a swarm of smaller objects separated from the main nucleus during the perihelion passage. If this phenomenon is confirmed, it would show that 3I ATLAS is not a single, solid object, but rather a complex, multi-component system. Understanding these intricate internal dynamics is absolutely crucial for accurately modeling the object's future trajectory and predicting exactly how it will interact with the solar system environment as it begins its long move outward into interstellar space. Amateur observations provide tremendous additional value because they are capable of capturing the large-scale structures that often extend far beyond the narrow field of view of professional instruments. These contributions, which are often coordinated through global networks of experienced observers, allow for crucial continuous monitoring of the object's brightness and shape. They are often the first to detect transient events, such as sudden, unexpected increases in brightness or the appearance of entirely new features in the coma, which would indicate localized eruptions or fragmentation events. Combining this dedicated amateur data with the precise professional measurements creates a truly comprehensive picture of the comet's evolution over time. Scientific analysis is also greatly enhanced by precise imaging geometry. The very appearance of features like the anti-tail fundamentally depends on the relative positions of the Sun, the comet, and the observer on Earth. By taking images at different phase angles, researchers can confidently distinguish between structural features that are genuinely intrinsic to the comet and those that merely arise from projection effects. This careful geometric analysis is essential for correctly interpreting the anti-tail and accurately mapping the distribution of material within the coma. The interpretation of all these observations has, as you might expect, sparked considerable discussion within the scientific community. Some researchers suggest that the unique teardrop shape of the coma is directly associated with the presence of those non-volatile microscopic fragments. Others emphasize that perfectly natural mechanisms, such as anisotropic outgassings, where gas jets are released unevenly, or the radiation pressure sorting of dust particles, can produce very similar visual features. The ongoing accumulation of precise imaging, spectroscopy, and astrometry is essential to distinguish between these possibilities and develop the most robust understanding of the object's true structure and behavior. Finally, it's vital to acknowledge the distinction between verified scientific findings and the speculative or unverified content that circulates online. Recently, artificial intelligence has unfortunately been used to generate videos impersonating scientists and presenting misleading information about 3i-ATLAS. These videos, which often cleverly blend factual data with false claims, pose a serious challenge for the public in discerning credible information. The scientific community strongly emphasizes the importance of relying exclusively on verified observations, peer-reviewed publications, and official releases from recognized institutions like NASA and ESA to maintain accuracy and credibility in reporting. The case of 3i-ATLAS perfectly exemplifies both the enormous opportunities and the unique challenges of modern astronomy. On one hand, it offers an exceptionally rare chance to study a genuine interstellar object in fantastic detail, capturing its morphology, composition, and dynamics. On the other hand, the proliferation of digital media and AI-generated content requires continuous vigilance to ensure that our interpretations remain based on irrefutable evidence and sound scientific methodology. For anyone who wishes to follow the object in real time, the best approach is to consult those primary sources, the official Hubble Image releases, ESA updates, and coordinated observation campaign reports. Looking ahead, the scientific community eagerly anticipates further insights. The ultraviolet spectroscopy data will provide detailed compositional information. Continued imaging will track changes in the coma and the anti-tail. Astrometric monitoring will refine the object's trajectory and rigorously test the models of non-gravitational acceleration. And amateur contributions will continue to extend observational coverage, particularly for large-scale features that professional instruments may not be able to capture in a single frame. Collectively, these efforts will profoundly deepen our understanding of 3i-ATLAS and interstellar comets as a class. In conclusion, the new Hubble image of 3i-ATLAS represents a truly significant step in our observation of this mysterious interstellar object. It confirms the existence of the Sunward Anti-Tail, which aligns perfectly with predictions about separated, non-volatile fragments and provides a robust framework for interpreting all ongoing observations. Combined with the global efforts of both professional and amateur astronomers, it offers us a once-in-a-lifetime opportunity to study the behavior of an object that originated from far beyond our solar system. As further data, including that ultraviolet spectroscopy, is released, the scientific community will continue to refine the models of 3i-ATLAS's composition, dynamics, and structure, offering both immediate insights and a long-term understanding of these rare interstellar visitors. The study of 3i-ATLAS is a powerful reminder of humanity's ability to track, measure, and interpret objects across unimaginable distances, and the crucial importance of distinguishing established scientific fact from circulating misinformation. The journey of 3i-ATLAS through our solar system continues, and with every new image, spectrum, and measurement, we draw closer to understanding the true nature of these quiet cosmic travelers.